time. So what's the difference between auditory filter and masking patterns? So here we see bottom here, this is a masking pattern. And up here we see a bunch of different, a few auditory filter graphs, transfer functions. So let me ask you this question. Which one can we actually see it? Is it auditory filter or a masking pattern? So if you open up a cochlea of an animal or something, and if you can actually see it, if you actually see it, the excitation and everything inside happening inside the cochlea, which one do you see? Is it masking pattern or auditory filter? The answer is masking pattern. Masking pattern is also alternatively you can call it excitation pattern. So it basically shows us how the basilar membrane makes excitation in response to an incoming sound, incoming tone. So as we see here, when a 1000 hertz tone is coming in, we see that the y-axis relative excitation level. So here the excitation is maximum at around the location of 1000 hertz, and then as the frequency, as the location along the basilar membrane is far. As it is far from 1000 hertz location, then we have less and less excitation, like this, and less excitation. So this x-axis is this is not a frequency of the incoming tone, but this is more about the frequency or the location corresponding to each frequency along the basilar membrane. That's a better way to understand. So again, this is when a fixed tone is given at 1000 hertz, then this is the excitation, the pattern of excitation we see. This is a masking pattern. Then where is the auditory filter? Then can we see auditory filter? No, auditory filter is more like theoretical model to explain the fundamental unit of processing of each frequency of tone. So now we have understanding that whenever we listen to a sound with frequency, the processing in the basilar membrane is limited to only certain frequency. So we have several filters. We are using those filters, and when we are given a tone of a certain frequency, then we use that filter, and for other frequencies we use other filters. So that's the concept of auditory filter. So we cannot really see it. We just have this model to explain other phenomena. So here, when you look at this masking pattern or excitation pattern, then where is the auditory filter? The answer is the whole graph. This one whole graph of excitation pattern reflects bunch of different auditory filter outputs. So that's what we see here up here. When the tone is so the point, the peak point marked at C here. This is basically the location when the tone is given, 1000 tone is given at this location, then we see this best output, filter output. So this y-axis up here, this relative gain, this is filter output. So this is the maximum. And if you look at B, what this means is if we were to try to use filter designed for the frequency designed to detect the frequency around this location, which is about 900 hertz, then we are using this next filter on the left. Then this output of the filter at the location for the frequency of 1000 hertz. For this other filter, this is B. So this B point comes here, and accordingly A point means that if we were to use another filter that is designed to detect or process the tone, which is this about 750 hertz, then the output of this filter is A. It is low, but because it is far from the center frequency. Anyway, so this is the A. This is the amount of gain we expect from this filter, meaning that down here, still tone is 1000 hertz. It is always fixed, but because of this excitation pattern as a result of combination of a bunch of different auditory filters, we are seeing excitation of about negative 40 dB from the top, which is A here. So that's how these two graphs, the two panels up and down, are related. So again, the answer here is if you look at a masking pattern or excitation pattern, that just shows us the combination or the result of a bunch of different auditory filters. Let's go back to slide 4. This is the masking pattern graph that we talked about before. So each of these curves represent a masking pattern or excitation pattern given a tone, given a masker located right here about in this figure, I think 440 hertz. So as we change the level of the masker from 20 dB SPL, 30 dB SPL, and so on, we have these bunch of different masking patterns we see. Here, one thing we consider here is, as we considered before, and we are doing again today, is something called the growth of masking. Meaning that as we change the level of the masker, as we increase the level of the masker, how much masking actually grows. So that's called growth of masking. So this figure shows not really growth of masking directly, but we can figure that out because when the masker level was 20 dB SPL, masking was about here, and the mask, which is what? About 4 dB, right? And the masker level was 30 dB SPL. The masking is about what? 13 dB, and the masker level was 40 dB SPL. The masking is 24 dB, and so on. So as we change change the masking levels this way, 20, 30, 40, 50, 60 dB SPL, and so on, we see the increase of masking, or the growth of masking in dB that way, like 4 dB, 14 dB, 24 dB, 34 dB, and so on. So that's called masking. No, that's called growth of masking. So next, growth of masking more clearly. So these are some typical results of forward masking. So now remember forward masking, the longer the signal delay between masker and the signal, or masker and the tone, we have less and less masking. So as we increase the masker, signal delay, you see less and less masking. So left panel is about that. But also another thing is for these different lines, 27, 37, 47, and so on, these represents result with different bunch of different masker levels. So 27 dB SPL, 37 dB SPL, and so on. These numbers mean the level of the masker. So we see how the masking grows. So if you look at this, the right panel, now finally we are looking at that. So now we look at the signal threshold, which is the amount of masking. Just understand the same way. Y-axis is amount of masking. X-axis is masker level. So as we just said, as we change the masker level, how the masking grows. So that is shown here. So as you can see, on the right panel, we have 3 curves representing 4 different numbers, 17.5, 27.5, 37.5. Where are these from? These are basically the 3 different signal delays we had on the left panel. So we kind of regrouped the data points here from left to right. Do you follow that? Left panel was a function of signal delay with additional parameter of mask level. On the right panel, the same data, but it is a function of mask level with additional parameter of signal delay. So basically the data represented here on the left panel, right panel are exactly the same, but they are shown in different ways. So you should be able to follow that. The point, important point to remember here is that masking grows as signal level grows, but it is not exactly linear. It is actually non-linear. So meaning that when the mask level increases by 10 dB, the signal, or I'm sorry, the amount of masking does not increase as much as 10 dB, but it is actually increasing less than 10 dB around here and more than 10 dB around here, when the signal mask level is high. Just moving on, graph of growth of masking for forward masking. In earlier slide, we didn't specify what the mask frequency and the probe frequency are. Here in this graph, we are looking at 2 different mask frequencies. When the if we have probe tone, the target tone, which is 6,000 hertz, and the mask is also 6,000 hertz, then we have this black markers, lines connected with black markers. So this pattern of growth of masking is linear, so meaning that for the increase of a given increase of mask level, we have same increase of the amount of masking. But when the mask frequency is different from the probe frequency, the growth of masking is not linear. And so we can see here in this open circle graph, open circle curve here. Obviously, because mask and probe frequencies are different, masking does not begin until the mask level is quite high. So, but once it starts, the growth of masking increases quite abruptly. So it is quite nonlinear. So we see both linear growth of masking and nonlinear growth of masking. This is the final slide for the topic of masking. So we've been talking about auditory filters, masking patterns, and also psychophysical tuning curves. So now we consider what happens when hearing loss is present. So how does it impact? How does it affect these auditory filters, psychophysical tuning curves, and masking patterns? So here, psychophysical tuning curve first. In normal condition, we have sharp tip. The bottom part is relatively sharp. That sharp tip helps us to focus on certain frequencies. So with cochlear hearing loss, the first thing we see is the sharp tip is gone. It is lost, meaning that the sharp, accurate, precise tuning for frequency is lost. Also, the location of tip may be shifted from the original frequency to other frequencies, and so or sometimes we have double tips. So as opposed to a single sharp tip, we may have broadened tip. So it's not really considered tip anymore. So it just broaden part of the broaden bottom or something, or it is largely, it can be shifted, not at the accurate precise frequency. If you look at auditory filters compared to auditory filters in normal hearing, for cochlear hearing loss, first of all, the filter bandwidths are broadened. So then how much is it broadened? It really depends on the degree of hearing loss. Meaning that someone with cochlear hearing loss may have broadened bandwidth of the auditory filter, or in other words, ERB, which is equivalent rectangular bandwidth. So meaning that remember, when two tones are played, if the two tones are falling into one single auditory filter, then we do not perceive them as two separate tones, but rather one tone. So for people with hearing loss, people with cochlear hearing loss with broadened auditory filters, their perception of two tones that are close to each other may be different from normal hearing listeners' perception. So for the tones that normal hearing listeners easily differentiate or perceive as separate tones, may be perceived as one single tone, but kind of hodgepodge, not sure. So there's some amplitude variation, but the frequency is not sure, something like that. So there is implication of cochlear hearing loss. So this means that when multiple sounds are going on, then people with cochlear hearing loss have reduced ability to segregate the components of the tone, components of the sound. So this is one reason that people with cochlear hearing loss may have additional difficulty understanding speech in the background noise, because normal hearing listeners, when we listen to speech sound in the background noise, as long as the noise level is not really overwhelmingly loud, we are able to differentiate the target sound in the background relatively easily using these auditory filters. So we are able to focus on specific auditory filters and try to ignore others. But as the auditory filter gets broadened, that segregation of components based on auditory filters is not going to work as effectively. Okay, this is it for the topic of masking.